All right, so we spent a little while working on regular polynomials. We have learned how to find real zeros. We've learned how to find complex zeros. Let's find out what happens if we start to combine these polynomials in new and interesting ways. Here's what we're going to do. We're going to break up section 4.6 into several days, and they're all about something called a rational function. Here's the idea with a rational function. Let's step back a second. You may remember, actually you better remember, that a rational number is a number divided by another number. It's a number that can be expressed as a fraction or a ratio, hence the name. A rational function is going to be a function divided by another function. Now the two rules here is that f and g, both of those functions, need to be polynomials. And that g of x cannot equal 0 because you can't divide by 0. The reason why rational functions are interesting is because they have a quirky behavior that polynomials definitely do not do. They have something called asymptotes. An asymptote is an imaginary line on a graph that a function will approach. And we can have vertical asymptotes, we can have horizontal asymptotes, we can have slanted asymptotes, we can have all kinds of different kinds of asymptotes. What we're going to get into today is vertical ones. But first, let me show you what this looks like. I'm going to graph up a function real quickly. Y is equal to 2x squared plus 16x plus 30 divided by x squared minus 9. Okay, if I graph this up, I've got it here on my first line. You can see 2x squared, 16x, 30, x squared minus 9. One thing that's worth pointing out is that I've got parentheses around my numerator and my denominator. You don't want to forget that. Otherwise, your calculator is going to think you're doing 2x squared plus 16x plus 30 divided by x squared and then subtracting 9, which is clearly going to give you something goofy. So, when we graph this, we get this behavior. What we have here is the graph seems to level off on the left-hand side. We can see it's starting to level off on the right-hand side. It's approaching something called a horizontal asymptote, which we'll get into later. However, what we're getting into today is this. This thing where like the graph just seems to keep getting closer and closer on the left-hand side and closer on the right-hand side. Now, that asymptote, that imaginary vertical line right there, is drawn by your calculator in a desperate attempt to try and connect a bunch of dots that are really far away from each other. But if you graph it on something with better resolution than a TI, it won't actually show up. What I'm going to do today with the vertical asymptotes is instead of chatting about why they exist, first I'm going to show you how to find them, and then once you know how to find them, then why they exist will make a little bit more sense. So, how to find vertical asymptotes. Okay, in math class, VA stands for vertical asymptotes. I'm not talking about how to find the Office of Veterans Affairs. That's vertical asymptotes. First thing you want to do is you want to factor the top and the bottom. When I say top and bottom, I mean the numerator and the denominator. You want to keep it real, okay? You don't want to be getting into imaginary numbers here. We're only talking about things in the XY plane. They're all real numbers. 2, you want to cancel factors if possible. Then terms that make the denominator equal to 0, they produce a vertical asymptote. I guess if I were being really formal, I would say factors that make the denominator equal to 0, but I think you get what I mean. Now, when we cancel these factors here, those factors, if we cancel them out, they are going to produce a feature of the graph, but it's not a vertical asymptote. What those canceled factors produce they produce holes, okay? So we have holes that can be produced by these factors, and we have vertical asymptotes that can be produced by these factors. Either way, we wind up with some factors in the denominator that could make it equal to 0. Therefore, the domain has to exclude them. Okay, so let's try one out real quickly. We'll start simple and then we'll move up to a couple that are a little bit more complex. Y is equal to x plus 2 divided by x squared minus 2x minus 3. First step is to factor the top and the bottom. X plus 2, there's nothing to be done there. X minus 3 times x plus 1. Okay, now we want to try and factor out any terms, or cancel out any terms if we can. There's no factors here that cancel out, that would produce a hole in the graph. I didn't want to play holier than thou on the first one. So, no holes. So what's left is this x minus 3 and this x plus 1. So that tells us that we have vertical asymptotes at x equals 3, x equals negative 1. The domain cannot include those values because you can't divide by 0 here, you can't divide by 0 because of that x plus 1. Now, I'm going to pause here to note something. You may remember during the first semester that I harped on the fact that the domain gives you x values. Some people had a tendency to write something like this: the domain cannot be 3 or negative 1. The domain is not the x values. The domain is the whole group of x values. It's not that one particular thing. So the domain doesn't actually equal any one particular number unless it's a really restricted one. The same thing goes for the vertical asymptote. A lot of people tend to sometimes write vertical asymptote equals 3, negative 1. The vertical asymptote is a feature of the graph. It is a imaginary line. It is not a number. Okay? The numbers are the address of the vertical asymptote, so please do not fall into this trap. It's kind of a pet peeve of mine to say that a vertical asymptote is equal to a number. It's kind of like saying a person is equal to their age. Their age is a feature about them, but it's not what they are. Same thing here, the vertical asymptote is at x is equal to 3, x is equal to negative 1. The vertical asymptote is not equal to 3. Okay. Well, now that we've seen the deal here with vertical asymptotes and how to find them, let's discuss briefly on why they exist. Why do they happen? Well, you may have noticed that what we were looking for was where the denominator was equal to 0. Well, when the denominator is equal to 0, let's see what happens when the denominator gets really small before it equals 0. Let's say we have 5 divided by 10. Okay, just an arbitrary number. I picked 5. I divided it by a number that's bigger than it, 10. We all know that's equal to 1/2. Let's say 5 divided by 0.1. That's 5 divided by 1/10. that is equal to 50. If I do 5 divided by 0.001, that winds up being 5,000. So we have 1/2, 50, 5,000. If your denominator gets smaller, so as your denominator approaches 0, what happens is your fraction here gets very big. And that's what happens at a vertical asymptote. Because a vertical asymptote is where your denominator would equal 0, as you start to get close to that x value, the value of your function becomes huge because you're dividing by a very small number. That's why when we graph it, we wind up having 4 options at any given vertical asymptote. Generally, we'll wind up using 2 of them. From the left side, your function can either increase without bound, f of x approaches infinity. As x approaches a, that's what I'm going to call the x value where this asymptote is, as x approaches a from the negative direction. So I'll put a little minus there. When you get into calculus, you'll refer to this as a left-hand limit. Don't worry about that right now, talking about limits, you got a while. But we're approaching it from the left-hand side. From the left-hand side, you could also have your function decreasing without bound. It could, f of x could approach negative infinity. Of course, it can't do both at the same time because your function still has to pass the vertical line test. So it's either going to increase without bound or it's going to decrease without bound, but it's not going to do both. You can also have the same thing from the right-hand side. Your function, as x approaches the value of your asymptote from the right-hand side or from the positive direction, so we'll do a little a plus, then your function could increase without bound, or it could decrease without bound. So, and the same restriction applies where it's going to do one but not both. So you have these couple of different options that can happen. So now that we've explained that, let's go into why these, or a couple of examples on how these can occur in various different combinations. F of x is equal to x squared minus 16 over x plus 4. All right, first step is to factor the top and the bottom. Nothing to factor on the bottom. That x squared minus 16 up top, though, should jump right out at you as a difference of squares. X plus 4 times x minus 4 divided by x plus 4. Okay, our next step is to cancel any factors we can. Boom, boom. X plus 4 cancels out. This tells us that we have a hole at x is equal to negative 4. This also tells us that since we can't divide by 0, we have the domain is everything but negative 4. So notice how the domain is everything but the hole. What's left is this x minus 4. X minus 4, if we graph that, what we'll get is a line, slope 1, y-intercept negative 4. So if we graph this, what we'd expect is the graph to look kind of like a line, but it's going to have a hole at x is equal to negative 4. So let's test it out. I'm going to clear out that graph so that we're not looking at it. And y3, I've got it already plugged in. X squared minus 16, x plus 4 in the denominator. Notice again, I've got parentheses here. If you ignore your parentheses, you're going to get the wrong answer. You're going to get the wrong graph and you're going to get confused. So don't forget those parentheses. If we graph this, lo and behold, it looks like a straight line, but it's deceptive. Use my calc menu, find out the value when x is equal to negative 4, and sure enough, x is equal to -4, y is nothing. There's no y value there because there's an actual hole in my graph. You just can't see it because the resolution on the TIs is not that great. Okay, let's go back to our first example. I'm going to reuse that function that was the first one that I showed you. 2x squared plus 16x plus 30 divided by x squared minus 9. Okay, first step, anytime you factor is to pull out a greatest common factor. Up top, you can pull out a 2. So I've got 2 times x squared plus 8x plus 15, and my bottom is x squared minus 9. Okay, now we can finish this up. X squared plus 8x plus 15 is x plus 3 times x plus 5. Denominator, another difference of squares, x plus 3, x minus 3. Okay, so let's see what we have. We cancel out the x plus 3. So we know we have a hole at x is equal to -3. However, the x plus 3 is still in, or x minus 3 is still in the denominator. So that tells us we have a vertical asymptote at x is equal to 3. Again, notice how I'm saying where the vertical asymptote is. I'm not saying the vertical asymptote is equal to 3. The domain has to exclude both of those numbers because both positive or -3 would make my original denominator equal to 0. So I can't have that. So x cannot be positive or -3. All right, so if we graph this, what we're going to expect is we're going to expect to see only one vertical asymptote. We go back to that. Graph that one. I don't want to graph that one. There's my vertical asymptote at x is equal to 3. And what happens when x is equal to -3? I have a hole. I do not get a y value. So it works out. So now that we know how to do this, and a lot of these basic skills you've got from finding the domain of functions last semester. Here's what I want you to do. Your practice is going to be on page 404, and I just want you to find the domain, vertical asymptote, and the holes for the functions given in numbers 1, 5, and 9. Disregard what the directions say, just look at the functions and find the domain, the vertical asymptotes, and the holes. Good luck, and I'll see you in class.